Hey there, we're going to finish up this unit on radicals and inverses and relations by looking at rational exponents. So we created rational exponents when we learned a shortcut to simplify nth roots. We took the power, which was generally under the radical sign, which didn't have to be there, but it's generally there, and we divided it by the index, the number that indicates which root we're taking, okay? And we kind of created our own fractions, right? And we looked at that and we did a division on it, and we said, okay, well, it can help us figure out how many groups of the right size we can take out, and then how many have to stay under the denominator. Well, we're going to use fractional exponents again, and then we're also going to use the same rules of exponents that we use for integers with rational expressions, rational exponents, okay? So the first thing we want to do is we want to write a radical as an exponential expression or as a rational exponent. And to do that, we take the power, which is generally under the denominator or to the right of under the radical. And the index is which root, or it's the root. Okay, and we make a quotient out of those two. So in radical form, we would have the nth root of b. In rational form, we would have b raised to the 1/nth power, b to the 1/nth. So if I had the square root of 5, that would be 5 to the 1/2 power. If I have the cube root of 3, that would be 3 to the 1/3 power. If I had the fourth root of 10, that would be 10 to the 1/4 power. And we don't have to have just numerals underneath our radicand. We can have variables and exponents like that. So this b would be written as a rational form as x to the 3/2. This is understood to be a 2 when there is no number there. All right, c, this is 2 to the 1/2, x to the 2/2, and we can simplify that. The 2 to the 1/2, no, that's as simple as we can get. But x to the 2/2, that can be written as x to the first. And then think about our even, odd rule. So we would put absolute value bars around that x, all right? We can go the other way. We can write an exponential expression, all right, as, or rational, we can call it, as a radical, all right? So basically I take whatever is in my numerator, that stays with my base under the radical, and then my denominator part of my exponent, that's my index, okay? And if I wanted to write y to the 7/4 in radical form, my y and my 7 would stay under the radical, and my 4 would be my index. Now I just want you to know that it doesn't matter whether you write it like this or if you write it like this. They mean the exact same thing, okay? And a lot of times when we evaluate, we actually apply our index first and then we raise it to a power, okay? And then 2x to the 1/2, this can just be written as 2x to the first. All right, we don't need that, but I'm just showing you how it plays out. And then my index would be a 2. Okay. So I want you, these are your video questions. I want you to go ahead and work these out, and then you can come back if you got any of them wrong. You can see what happened. All right, so this is the fourth root of x, so I'm going to write this as x to the 1/4 power. This is 3 times the cube root of x to the 4th, y to the 5th. So this is going to be 3, x to the 4/3, y to the 5/3. Remember, it's power over index, power over index. Going the other way, this 9 in my denominator, that's my index, so I get the ninth root of a to the first. You don't have to have the 1 there, just letting you know where each piece goes. And this one is the square root of x cubed. This is not necessary, so we could just write it as the square root of x cubed. Make my 3 a little smaller so it looks like a power. There you go. Right? When we're evaluating, like I mentioned a little bit ago, it's easier to apply the index first because it gets your number smaller, and then you can power it up. You can also do this on your calculator, and I'll show you that when we get into class. And then when you're simplifying rational exponents, even if your base is a number, you're going to want to apply these if it's necessary. When we're multiplying like bases, we're going to add the exponents. When we are dividing like bases, we're going to subtract the exponents. If we're raising a power to a power, we're going to multiply exponents. We're going to move all negative exponents to the other level, just like we did before, and we're going to rationalize our denominators. Make sure that we have no fractional exponents in the denominator. We have to apply a power that takes us to a whole integer. All right? All right, so if I wanted to find the fifth root, or 3,125 raised to the 1/5 power, this is the same as this. Okay, if something ends in a 5, I'm going to start looking for if it's 5 raised to a power, and it is the 5th root of 5 to the 5th, so that gives me just 5. Okay, this is the 8th root of 256, and then we're going to cube it. Okay, and so this is 2 to the 8th, so this is the 8th root of 2 to the 8th, and then I'm going to cube it. This cancels, so I get 2 cubed, and I get 8. All right, you can also do this on your calculator. Now, with this, I'm multiplying like bases, so what I want to do is I want to add those exponents together before I start evaluating, and that just gives me 3 to the first, which equals 3. Whoops, put the wrong thing there. I might get rid of these extra lines here. Okay. Now, if I'm taking negative 27 to the 2/3, this is the cube root of negative 27. Then I'm going to square it. Negative 27 is a perfect cube. That's going to be the cube root of negative 3 cubed. And I'm going to square that. So I get negative 3 squared, which is 9. You just have to be careful with negatives and your nth roots. Okay, this is an odd nth root, so we're good to go. All right, now we want to write each expression in simplest form, and we want to assume that all variables are positive. Okay, that means that we don't have to know absolute value bars. Let me write that again. No absolute value bars. We don't need it because they're telling us all of them are positive. If it didn't say that, we would have to apply the even, odd rule. Okay, so this is p to the 1/4 plus 9/4 because I have like bases and I'm multiplying them. So that's p to the 10/4. Okay, and then I'm going to simplify. That's p to the 5/2. Okay. Now I'm going to simplify r to the negative 3/8. Okay, I can't have a negative, so this is 1 over r to the 3/8. Now you have to think about this. I have 3/8. That leaves us with a radical in the denominator. Okay, I can't have any fractional exponents in the denominator. So what do I have to add to 3/8 to get it to 1? Well, I need to add 5/8. So I'm going to multiply top and bottom by r to the 5/8. And I get r to the 5/8 over, that doesn't look good. r to the 3/8 times r to the 5/8 is r to the 8/8 or just r. Okay, you have to know your fractions, okay? Know how to add fractions, know how to subtract fractions, know how to multiply fractions. All right, we have y to the 1/7 times y to the 4/7. So that becomes y to the 1/7 plus 4/7 is y to the 5/7. It's not negative, there's no perfects in there, so I'm done. Number 4, you're going to apply this 1/2 to every single factor. Okay, so I'm going to have 18 to the 1/2. That's like the square root of 18. R to the 8 times 1/2, or 8 over 2. 50 to the 1/2. S to the 12 over 2. All right, so if I simplify the square root of 18, well, we know that that's 3 square roots of 2. So I have, and this is just 2 to the 1/2. So I have 3 times 2 to the 1/2. Oh, I need a little bit more room. So I have 3 times 2 to the 1/2 times r to the 4th over 50, square root of 50, well, that's 25 times 2, so that's 5 times 2 to the 1/2 times s to the 6th. These cancel, and I get 3 r to the 4th over 5 s to the 6th. Okay. All right, an application of this comes in inflation or compound interest. The future cost, capital C, of a product due to inflation is given by this expression right here. Capital C equals little c times 1 plus r raised to the nth. In the formula, little c is the present cost, the cost today. R is the inflation rate expressed as a decimal, and N is the number of years. Okay? What is the exponent on little c? Well, it doesn't take a lot of investigation. That little c is not getting the N. It has an exponent of 1. Which expression does get the exponent of N? Well, that is the expression 1 plus R. Now, if N equals 1 is 1 year projection, what would N equal 1/2 imply? Well, that would be 1/2 a year or 6 months. What would N equal 3/4 be? Well, that would be 3/4 of a year or 9 months. What would N to the 3/2 be? Well, that would be 1.5 years. Okay? So let's try this. The future cost C of a product due to inflation is given by the expression C equals little c, 1 plus R to the nth. In the formula, little c is the present cost, R is the inflation rate expressed as a decimal, and N is the number of years. If a set of tires costs $390 now, what would it cost in 6 months if the inflation rate is 5.3%? All right, so we're looking for big C. Little c is $390. The interest rate is 1 plus 0.053. 6 months is raised to the 1/2 power. So when we put that into our calculator, we get $400.20. Why don't you try the very first part, not the A or the B, but the very first part of number 2. All right, C is equal to 329 times 1 plus 0.053 to the 3/4, or to the 0.75, and that's going to be $3.42. Okay, $3.42. So what is the amount of increase in the price? Well, you take the new price minus the old price, and that's $3.42 minus $3.29, and that gives us 13 cents. How do I find a percent of change? What is the percent of change in price? Well, that is new minus old, new minus old, divided by the old, or you could think original, and that's going to give us new minus old. We already calculated 0.13 divided by 3.29, and that gives us 3.95%, I believe. You're going to multiply that by 100 to write it as a percent. So that is 3.95% change. All right. This is our daily assignment. Thanks for listening. I'll see you tomorrow.